All right. Hi, everyone. So, to begin, we need to firstly reflect on our development process. So, our first major error was a massive 190,000 RMSE. So, this was a session state failure where we were engineering features on top of existing ones without a clean reset, and which really corrupted our feature matrix and created significant data leakage.
After we reset, we faced the over pruning trap where we tried to be aggressive by removing 15 outliers, but our score ended up dropping to 18,248. This was a turning point where we realized we were increasing the model's bias and losing the signal we needed to generalize.
So after this, we eventually shifted to the surgical pruning. So really removing only the two extreme outliers with GRLI area, which is greater than 4,000 square feet. This really restored our baseline and allowed us to implement symmetric log targeting to really normalize the right skewed property prices, which the goal was to satisfy the linear assumption of a Gaussian target distribution.
To improve performance, we moved to a weighted quad blend, which worked well, but we hit a plateau at the 17,000 mark. So we analyzed the residuals and saw the models were still struggling with the nonlinear luxury curve.
So that's when we pivoted the stacked generalization. So by integrating that XGB regressor into a stacking regressor with a lasso CV meta learner, we really allowed the model to learn the optimal weights through the fivefold cross validation instead of guessing them.
Mechanically, this worked because the lasso CV meta learner enforces a sparse weight distribution, effectively silencing base models that contributed more variance than signal in specific price ranges. We also set a 50,000 iteration limit on our coordinate descent optimization to ensure our linear base models converge to a stable minimum where the gradient of the cost function approached zero, even within a high dimensional feature space.
So to assess the fit of our best model, we looked at our final output metrics, which the train RMSE were 0.0792, and our test RMSE, which would be 0.0834.
Analyzing this 0.0042 gap, which is a mere 5% delta, we diagnosed the model as well fitted. Underfitting was not observed as both errors remained low, and overfitting was mitigated as the generalization gap was minimal.
So in order to improve the fit, we addressed something that we call heteroscedasticity. So by implementing Huber loss in our gradients boosting components. So mathematically speaking, while squared loss amplifies large residuals quadratically, causing the model to really over prioritize luxury outliers. So Huber transitions to linear penalties for residuals beyond a specific threshold. So this reduced the gradient explosion and stabilized the final predictions across all price points.
Even with our strong performance, we identified creation level experiments to try and break the 15,000 barrier. Quantile regression stacking was one of them, which instead of predicting the mean, we could stack models that predicted different quantities to better handle the variance in the luxury market. We could test a Bayesian framework to assign weights to our base models, allowing us to quantify the uncertainty of each prediction. Or we could use the Shapley additive explanation values to prune features that contribute noise rather than just low coefficients, further refining our feature space. In conclusion, we made several final attempts to push into the sub 15,000 range using even deeper stacking. However, these attempts caused our store to regress back into the 17,000s, likely due to the model variances and overtuning to the training noise.
So our best performing regressor remained the meta stacking ensemble, which really achieved our peak score of a total of 16,484 approximately, as we can see here. So we really justified this as our most well-fitted model because it achieved a calibrated balance between nonlinear complexity and rigorous linear regularization. So our journey really demonstrated that in high stakes regression, the most complex model is rarely the most generalizable.